Welcome to the review for Physics 112. And this is the Thermodynamics unit. So we are going to review some of the topics that we discussed for thermodynamics. Before I start that, I just want to talk about the exam for just a moment. There will be a few pages of conceptual questions, which are basically taken from your homework. So in fact, they're exact matches to questions from your homework, mostly multiple choice, a few that you actually fill in a formula or something like that. So that'll be the first few pages. And then after that, there'll be, I don't know, 5, 6, 7 pages of problems where you work through the formulas, you derive the formula for the end, you plug in the numbers, you get a final result numerically, and you enter the answer with the units. And so on these will be partial credit. So you definitely, not only should you show your work, but you must show your work. If you just give an answer, even if it's right, if you haven't shown your work, then I'm not going to give you full credit. All right. So you've got to show your work. But even better than that, also important is that if you don't get the answer right, but you showed your work, then I can give you partial credit. So this also means that you need to have your work be legible and you need it to be followable. I need to be able to understand what you're doing in order to give you credit. So make your solutions logical and work from step to step going down the page. Don't just write things all over the page with um, no reason why you move from this place to that place to that place. Make it linear going from the top down to the bottom. Draw a column down the center, a line down the center of your page if you need to, go down the left side, then go up to the top of the right side, then go down and so on. Do things like that. Make it easy for me to follow your work. Okay, now you are allowed an 8.5 by 11 sheet of paper with formulas and constants on both sides of the paper if you want. So I don't limit you really on what you can put on there, except that you can't put solutions to problems, right? So you need to just put the formulas and the constants, and you need to know how to use them to solve problems. Let's see. I will give you some constants, the sheet of constants that was at the back of your syllabus. I'm going to give that to you for the test. So all of the constants on that sheet, you do not need to have on your formula sheet, but you can put them on there if you want. Let's see here. What else? Oh, you can bring a calculator. You can use a calculator on the test, but you cannot use your phone. Even if you use the calculator on your phone, you cannot use your phone. Not even for that. So no phones, no computers, just ordinary calculators. Um, okay. Yeah. Okay. Great. So it'll be Thursday. It'll be during lab time. You'll have the full 2 hours and 50 minutes, but I only designed the test to take about an hour. And indeed, some students start leaving after about an hour, but that's fine. You do not have to be one of those. You can take as long as you want. Every student, every person is different. How they approach the test is different. Some people like to check and recheck their solutions, others don't, whatever. It's up to you what you do there, but you'll have the full 2 hours and 50 minutes if you need it or want it. Okay, let's get into the first chapter. The first chapter was about temperature. And you'll recall that the first thing that we defined or discussed was the zeroth law. Oh boy, zeroth law of thermodynamics. And the zeroth law of thermodynamics states that if two objects, A and C, are in thermal equilibrium, so um, that means that there is zero net energy transfer from one to the other. So they're in thermal equilibrium if there's no net energy transfer between them, no heat transfer. And if two objects, A, the same A as before, and a new object, B, are also in thermal equilibrium, so that, again, there's zero net energy transfer between A and B, then this implies that the objects B and C are also in thermal equilibrium. So that is the zeroth law of thermodynamics. The reason why that's important to us is that allows us to define equal temperature. So we define equal temperature if the two objects are in thermal equilibrium. So if in thermal equilibrium. So in other words, since A and C are in thermal equilibrium, we have defined their temperatures to be the same. And if A and B are in thermal equilibrium, we have defined their temperatures to be the same. And the zeroth law of thermodynamics implies that B and C are in thermal equilibrium. Therefore, it also implies that with this definition, the temperature of B equals the temperature of C. So that makes it so that we have a consistent definition of equal temperature. Then, secondly, now that we have equal temperature, we can define higher temperature and lower temperature by looking at the direction of net energy transfer. So if the net thermal energy transfer, the net heat, is going from A to B, then we define the temperature of A to be greater than the temperature of B. All right, furthermore, this allows us to set a temperature scale, and you'll remember that we calibrated a thermometer at two different temperatures, like the freezing point of water and the boiling point of water, and then we used a linear scale in between them. Furthermore, you'll remember that we discussed the equal volume, the constant volume gas thermometer was a way to improve the temperature scale. And furthermore, we found that if we extrapolated the temperature all the way down to zero pressure, and we realized that it was impossible to go below zero pressure, that allowed us to define an absolute minimum temperature. That absolute minimum temperature we call the absolute zero. We found that was at negative 273.15 degrees Celsius. And it makes a lot more sense to define a temperature scale where that is the zero of the scale. So that allowed us to define a new temperature scale, which we call the Kelvin scale. And absolute zero, by definition, is 0 Kelvin. We then defined the temperature of the freezing point of water, which was previously 0 degrees Celsius. We define that as 273.15 Kelvin. And between those two scales, then we extended the Kelvin scale to all other temperatures. And we did this in a way such that the change in temperature on the Celsius scale is equal to the change in temperature on the Kelvin scale. So that is 1 degree Celsius change is equal to 1 Kelvin change. Okay. All right, so that was temperature. Then we discussed that when the temperature increases or decreases, most substances expand or contract. So if the temperature increases, typically a material expands, and if the temperature goes down, it contracts. And we found that the expansion of the solids and liquids, that a formula for the solids was that the change in length was proportional to the initial length, proportional to the change in temperature, and the constant of proportionality is called the coefficient of linear expansion. And we found that this formula is only valid when the change in length is very small compared to the initial length. So this is a formula that allows us to calculate and predict the change in length of a solid. And alpha, the coefficient of linear expansion, those are measured for various different types of solids, and they are tabulated, and so you can find them in tables in your book. And the table that's in your book, that's one of the tables I'm giving you, but you can also find these on the internet. Now, this does not work for liquids because liquids do not preserve their shape when they expand or contract. So unlike a solid, where a solid will keep its shape, but just expand in all directions, but keep its shape, a liquid, on the other hand, changes its shape to fit the container. So the change in length of a liquid depends on the shape of the container. So we can't have a universal number that's for the liquid. So for liquids, we need to think about the volume instead. So for a liquid, the change in volume is proportional to the initial volume and proportional to the change in temperature. The constant of proportionality, beta, is called the coefficient of volume expansion. And this formula only works when the change in volume is very small compared to the initial volume. And once again, we can tabulate these, and we have, and there's tables of these. There's a table in your book. That table I have, I'm giving you on the test, and you can find more of these coefficients on the internet. Okay, finally, so the first formula only works for solids, but the second formula works for liquids, but does it work for solids as well? The answer is yes. The coefficient of volume expansion for a solid is 3 times the coefficient of linear expansion for the solid. So that is a useful thing to know because if you're calculating the change in volume of a solid, you don't have to calculate each length individually. You can just calculate the change in volume in one go. You just use a beta, which is 3 times the alpha, the coefficient of linear expansion. Okay, next we talked about the ideal gas law. And we learned the ideal gas law in 2 forms. The first form was pressure times volume equals number of moles of gas times universal gas constant times the temperature. So R, the universal gas constant, is 8.314 joules per mole Kelvin. And this formula is valid when the number of moles N is the thing that you know. On the other hand, sometimes what you know is the number of molecules. And so the formula for that is pressure times volume equals number of molecules times Boltzmann's constant times the temperature. Boltzmann's constant is the universal gas law divided by Avogadro's constant. And you can put it into your calculator and you find 1.38 times 10 to the minus 23 joules per Kelvin. So this is the ideal gas law, and this is the formula that replaces Newton's law for gases, right? So in Newton's law, you'd have to keep track of every single individual molecule, but there's just way too many of them. So that would be impossible. And that's not even the information that you care about for a gas. So the information you care about for a gas is the pressure, the volume, the temperature, number of moles of gas, and so on. So this is called the state equation for an ideal gas. It's an equation that relates the various state variables. State variables are the variables that tell you everything about the gas. So if you know the pressure of the gas, the volume, the temperature, and the number of moles, you know everything about the gas, at least at a macroscopic level. And this is the equation that relates them. Okay, our next chapter was about the first law of thermodynamics, and we started with specific heat and calorimetry. So we learned that the amount of heat that you had to put into a substance um, was, let's see here, the amount of heat was equal to, proportional to the mass that you were trying to heat up, trying to change the temperature of. It was proportional to the change in temperature, and the constant of proportionality C is called the specific heat of the substance. So there's a different specific heat for each type of substance, each material, each metal, each liquid, and so on. So this is the amount of heat required to change the temperature of a substance. Now, this is with the assumption that um, the substance is not changing phases. Okay, so this only applies within a phase. So for example, for water, you're going to have a different specific heat for the frozen, the solid type of water, which is ice, and a different value for the liquid form of water. You'll also have a different value for the gaseous form of water, which is steam or water vapor. Okay, the specific heat, that's also, you can find these in tables. And so there's a table in your book with these. And that table I am also giving you for the test. Now, when it comes to gases in general, the specific heat will depend on the process, whether it's at constant volume or constant pressure or something else. We will discuss those more generally later, but you can find a few gases like water vapor um, in this table as well, and that's because that's focused on water vapor in the atmosphere where you're holding the pressure constant. So those versions are the constant pressure type. Okay, so that's within one phase, but what if we change phases? What if we change the phase of a material? Well, in that case, during the phase change, the temperature does not change, but you still have to put heat in anyways to get the phase to change. So this is called the latent heat. So up here, this was the specific heat. Now we're talking about latent heat. The word latent means hidden, and that's because they called it latent heat because even though there's heat going into the substance, the temperature is not changing. That's why they called it hidden. But the heat going in does make an effect. The effect it has is that it causes the substance to change phases. So if heat is going in, then the substance, some of the substance is transformed into it changes its phase to the higher phase. Okay, so the amount of heat required is proportional to the amount of mass that you heat up, that you change phase for. And then the constant of proportionality is L, is called the latent heat of either fusion means melting, or vaporization. So vaporization is when you turn it from a liquid into a gas. Now, L is the same going either direction. So if instead of melting it, you're solidifying it, L is the same. But delta M would be negative in that case because delta M is the change of the higher phase material. But you're decreasing the higher phase material, so it's negative. Again, L for vaporization is the same as L for condensation, but delta M is negative in that case as well. Okay, so between these two, you can find the heat required to both raise the temperature of a substance and change its phase. And you can go through multiple phases. You just have to take each piece one chunk at a time. All right, the next thing that we learned is the amount of work required to change the volume of a gas. And that formula was given by work is equal to, in fact, I'll do the differential work first. The infinitesimal differential work is equal to minus the pressure times the differential change in volume. We can integrate that to get the work is equal to minus the integral from initial to final point of the pressure times dV. And you'll recall that we discussed that the work is process or path dependent. Now, at first, that may seem a little surprising, but it shouldn't because the same thing is true in mechanics. So the work required to move a desk across the floor depends on the path through which you move it. So if you take a straight path, that's one work. But if you push on the desk, but the desk moves all over the floor, maybe because somebody else is pushing on it a different direction or against you or something, then you're going to do a different amount of work, even though the beginning and end points might be the same. So the work is depends on the path. And that's true in thermodynamics too. So if the pressure is constant, then you can pull the pressure out of the integral and you can do the integral. But if the pressure is not constant, then you can't. And so you need to know something about the pressure before you calculate the work. All right, next, we introduced the first law of thermodynamics. And you'll recall the first law of thermodynamics was a restatement of energy conservation in thermodynamics. If the internal energy of a substance changes, so if the internal energy of a system changes, that change is equal to the amount of heat going into the system plus the amount of work done on the system. So both of these are the amount of energy going into the system. And of course, if energy goes into the system, then the internal energy changes. It increases by the same amount. So this is just a law of conservation for thermodynamics. The change in internal energy equals the heat absorbed plus the work done on the system. All right, finally, in this chapter, we talked about some applications of the first law of thermodynamics. So this section was called applications, but mainly what this is considering what happens in various different special cases of processes. So we'll talk about each of those types of processes. All right, so the first one that we defined was an adiabatic process. And as we discussed in class, the definition of adiabatic is that the heat going into the system is zero. That can happen either because it's heavily insulated or because the process is so fast there isn't time for heat to transfer. Now, from the first law of thermodynamics, as we saw up here, that tells us that the change in internal energy for an adiabatic process is just equal to the work done on the process. So those are the things that we learned about. Let me just skip ahead here for a second and fill in some other details of adiabatic processes that we learned. We also learned that for adiabatic process, this was in a later chapter, that the pressure times the volume to gamma was constant during the adiabatic process. This implies that the initial pressure times the initial volume to the gamma equals the final pressure times the final volume to the gamma, where I remind you, gamma equals the coefficient the specific heat at constant pressure divided by the specific heat at constant volume. Okay, so those are also constants that are in a table in the book that I will give you on the test. And I'm going to discuss those again in just a moment. Okay, we also found a formula for the temperature times the volume. So it is the temperature times the volume to the gamma minus 1 is also a constant. It's a different constant than for pressure times volume to the gamma. But this implies that the initial temperature times the initial volume to the gamma minus 1 equals the final temperature times the final volume to the gamma minus 1. And these are formulas that are useful when considering adiabatic processes. All right, our next special type of process is An adiabatic free expansion. Actually, I'm going to go back to the last page for this. Adiabatic free expansion. And for this process, we learned that since it's adiabatic, the heat is still zero, and the free expansion part means that the work is also zero, and together these imply that the change in internal energy is zero. If it's an ideal gas, so this is a special case. If it's an ideal gas, then this also implies that the temperature does not change either. That's only for an ideal gas, though. Okay, so that is it for an adiabatic free expansion. Since it's adiabatic, it of course satisfies the equations up here, but we've added some additional things about it. All right, what about an isobaric process? An isobaric process is one where the pressure is constant. This implies that the change in pressure is zero. And if the pressure is constant, then we can calculate the work. Because the pressure is constant, we can pull it out of the integral. And so we can find the work done is minus the pressure times the change in volume for an adiabatic process. Furthermore, for the heat, we discussed in class that the heat absorbed by a gas during an isobaric process was in Cp delta T, where Cp is the constant, is the specific heat at constant pressure for a gas. And we're talking about a gas here. Okay, so now if we put both of these into the first law of thermodynamics, we find that the change in internal energy is equal to the heat plus the work. So therefore, it's equal to NCP delta T minus P delta V. And that is everything we learned about an isobaric process. Okay, next, we discussed an isovolumetric process. During an isovolumetric process, the volume is held constant. This implies that the change in volume is zero. If the change in volume is zero, we can say something about the work. It's also zero because the 2 points, the initial and final point, are the same. So on a PV diagram, that is going to be a vertical line which has no area under it. So the work done during an isovolumetric process is zero. The heat absorbed during an isovolumetric process for a gas is in CV delta T, where CV is the specific heat at constant volume for a gas. Now, of course, if it's not a gas, if it's a solid or a liquid, then the heat absorbed is mCp C delta T, where the C is the specific heat for the solid or liquid. By the way, that's also true up here. I should have said that up here. So Q can also be mC delta T. And in that case, the change in internal energy, well, let me put it over here. The change in internal energy here would be mC delta T minus P delta V. And same thing down here. So we have the two cases. So the change in internal energy is Cn CV delta T minus zero. The work is zero. And same thing here. Change in internal energy would be mC delta T. So you really have to choose the formula according to whether you're working with a gas or a solid or liquid. But anyways, that's an isovolumetric process. Okay, finally, an isothermal process. is one where the temperature is constant, which implies that the change in temperature is 0. Okay, and then for the special case where you're working with an ideal gas, then we also have that the change in internal energy must also be 0, which implies that the heat is equal to minus the work from the first law of thermodynamics. We calculated those and we found that they were equal to nRT natural log V final over V initial. But make sure to not forget the minus sign here in front of the work. So if you're calculating the work, it's minus that formula. Okay, so that was everything about an isothermal process. All right, so next we started the next chapter, which was kinetic theory of gases. Um, and one of the things that we learned was the equipartition theorem. And the equipartitions theorem says that um, basically when you store energy in a system, it shares that energy equally among all the degrees of freedom that are available for that substance. So when we think about like a gas, the different degrees of freedom that are available are the translational motion, just the fact that the molecules are zipping around the space. The rotational motion, the molecules can rotate on their axis, and the vibrational motion. So imagine the molecule, the atoms in the molecule are vibrating in and out, or for more complicated molecules, it might be angles which are vibrating and so forth. So, um, when you've got a gigantic number of molecules and some amount of energy, all the different available modes of motion that can contribute to energy, they're all sort of contributing, right? They're all, the various collisions and stuff just excite all the different energy modes. So they're stored equally. Um, so this theorem states that each degree, here I'll write degree of freedom as DOF, degree of freedom, contributes 1/2 kBT to the internal energy, and the possible degree of freedom are translational motion, rotational, and vibrational. Um, okay, so now, and then furthermore, we learned that let's see, uh, the internal energy of a gas is the number of degrees of freedom over 2 um, in R in R. Yes, that's the number of degrees of freedom. Good. And then from this, we get that the specific heat at constant volume is the number of degrees of freedom divided by 2 times R. And so this is our master formula for gases, for ideal gases. And to the extent that our gas differs from this, then it may not be an ideal gas. Um, all right, so let's think about some different types of gases. We have monatomic gases. Monatomic gases are gases where each molecule has one atom. So these gases are gases of noble gases. So they're like helium gases, xenon, argon, the noble gases, because they don't create bonds with other atoms. And so their molecules are just one single atom. So they're monatomic. Okay, because of this, the rotational, there's no rotations and there's no vibrations. because it's just one atom that's spherically symmetric and infinitesimal, as far as, at least as far as thermodynamics is concerned. So for this, from non-atomic gas, we expect there to be 3 degrees of freedom. That's for the translations. It can move in the X, Y, or Z direction. Every gas has 3 translational degrees of freedom. So this is the minimum. And so for a monatomic gas, we find that the specific heat at constant volume is 3 halves R. And that's equal to 12, let's see, 12.5 joules per mole Kelvin. Yeah, and so that's it for a monatomic gas. And so if a monatomic gas differs from that, then it's not an ideal gas. And to the extent that it differs, that's like if it's a percent away, then it's like a percent away from being an ideal gas. And so that gives you a good rough guide to whether something is an ideal gas. Okay, let's talk about some diatomic molecules. Diatomic molecules are, for example, oxygen in the air. Oxygen is O2, that's diatomic. Dia stands for two, so two atoms, diatomic molecules. So oxygen, nitrogen, and so on. And so the major components of air, nitrogen and oxygen, are diatomic molecules. Okay, now for a diatomic molecule, the specific heat at constant volume depends on the temperature. The reason for that is that quantum mechanics comes into play for rotations and vibrations. So if you go down to low enough temperature, then it's too low of a temperature to excite the rotational or vibrational degrees of freedom. So at very low temperature, then the number of degrees of freedom equals 3, and CV is again 3 halves R, which is, as we just said, 12.5 joules per mole Kelvin. Okay, so that's very low temperature. At intermediate temperatures for the gas, and exactly where the transitions are is different for each gas. At room temperature, by the way, nitrogen and oxygen, they act, let's see, I believe they act like they've got, of course, they've got translations. All gases have translations, but I believe they act like they also have vibrations. I'd have to look that up, and I don't have that sheet with me. Well, you know what? I can find it really quick. I think. So let's see here. Yeah, let's see. I've got the table. So diatomic gases, nitrogen, yes, and oxygen. Okay, so yeah. So they both act like they've got translations and rotations, but not vibrations. So let's just go through that. Okay, so for this, intermediate temperatures, you've got the 3 translations, motion in X, Y, and Z. And then for a diatomic molecule, you have 2 rotations. So you don't have 3 rotations because the rotations around the axis of the molecule don't count because it's infinitesimal in that direction and rotationally symmetric. So altogether, we have 3 plus 2, which is 5 degrees of freedom. So CV then is 5 halves R, which is, if we calculate this, it's 20.8 joules per mole Kelvin. And that's, if you look in your table for CV, for nitrogen and oxygen, it's very close to 20.8. So they've got both translations and rotations. Okay, high temperature. This is where you have translations, rotations, and you've got enough energy to excite vibrational degrees of freedom. Well, in this case, you've got 3 translations, 2 rotations, and now you've got 2 vibrations. The reason 2 vibrations is because you have 1 vibrational motion, but you count both the kinetic energy in that and the potential energy. So altogether, you have 7 degrees of freedom in this case, and CV equals 7 halves R, which is, let's see, plug it into our calculator, 29.1 joules per mole Kelvin. Okay, so that's a diatomic molecule. And now you know that the diatomic molecule can never go above 7/2 R. So if, in fact, if you have a specific heat at constant volume, which is greater than 7/2 R, then you've got a polyatomic molecule. Okay, great. Now what? Okay, we also learned from this chapter the distribution of speeds, molecular speeds of the gas. So this would be the translational motion. And we learned three different ways of characterizing the typical speeds. They're close to each other, but they're not exactly the same. We found the RMS speed, which is the square root of the average of the square of the speed. So the average is over the square. That's very important. The square root and the square don't cancel each other. The formula for this we found was 3 kBT over m. That little m is the mass of one individual molecule. And so if you have that information, you can use this formula, but typically what you know is the molar mass. And so instead the formula would be 3RT over capital M, the molar mass. So for example, the molar mass for hydrogen gas is 2 hydrogens. It's a diatomic molecule. And each one has a molar mass of 1 gram per mole. So the molar mass of hydrogen gas would be 2 grams per mole. Or if we were looking at nitrogen, one individual nitrogen atom has a molar mass of 14 grams per mole. Sorry, 7 protons, 7 neutrons, 14 grams per mole. So the molar mass of nitrogen gas, since it's a diatomic molecule, is 28 grams per mole, and so on. So that's a good way to remember it. Okay, then we have the average speed. And so that is equal to square root 8 kBT over pi little m, or square root 8 RT over pi molar mass. Again, the second formula is typically easier. And then we have the most probable speed, which is 2 kBT over the mass of one individual molecule, or square root 2 RT over the molar mass. Okay, so I've talked to you about the importance of canceling units properly, right? Don't just plug the numbers into your calculator and then just put the units that you want, because that is a very good way to make a mistake. And indeed, this is the place I find students make the most mistakes in their calculation, and they're off by anywhere between a couple orders of magnitude and 10 orders of magnitude wrong because they're not careful about units. Also, you should know that these speeds for a typical gas, at room temperature, are going to be in the tens to hundreds to thousands of meters per second. So if you're getting that the speeds are 10 to the minus 10 meters per second, you've done something wrong. Okay, or 10 to the 10 meters per second, also wrong. In fact, 10 to the 10 meters per second would be faster than the speed of light. So anyways, so you should also have some sort of idea of what is a reasonable value for these. Yeah, and it's between tens and thousands of meters per second. All right, but I do, I mean, if you don't learn to cancel units, you're gonna have issues somewhere along the line in the future. Okay, this was it for the kinetic theory of gases chapter. Next, we move to the second law of thermodynamics chapter, and we started by defining a heat engine. So a heat engine schematically has a high temperature reservoir. It has a low temperature reservoir, and the heat engine, the way that it works is that it draws heat out of the high temperature reservoir. It uses part of it to do useful work, like get your car to move forward or charge up the battery in someone's iPhone or other phone. And then the remaining energy it expels to the low temperature reservoir. We define the efficiency of this engine as what we get out, which is the work, over what we put in, which is the heat that we draw from the high temperature reservoir. And we found through conservation of energy that this is equal to 1 minus QC over QH. Then we then we said, well, we would like the efficiency as high as possible. We'd like to get it to 100%. So we imagined that we could build a heat engine, um, which which drew heat out of a high temperature reservoir and did an amount of work which was equal to that, right? With zero expulsion of heat to a low temperature reservoir. So this would have an efficiency of 100%, percent. And we learned that the second law of thermodynamics told us that that is impossible. Okay, so second law of thermodynamics, states that it is impossible to build a heat engine which draws a heat QH out of a high temperature reservoir and uses it to do an equal amount of work. Okay, so the second law of thermodynamics tells us that is impossible. And yeah, I don't know why it removed a bunch of stuff. So let's try that again. Okay, that's the second law of thermodynamics. That's the Kelvin-Planck form, because they were the ones who discovered this Kelvin-Planck form. All right, next we learned about a heat pump. So for a heat pump, we have a high temperature reservoir and we have a low temperature reservoir. And we would like to transfer heat from the lower temperature up to the higher temperature. Now, you know that's not the natural direction that it flows. So we have to insert a heat pump. And the heat pump, the way that it works is some amount of work is done on the heat pump. And then the heat pump uses that work to draw or pull heat out of the low temperature reservoir and expel it into the high temperature reservoir. So we have to do work on the heat pump, and then the heat pump uses that work to get heat to transfer from low temperature to high temperature in the opposite direction which it naturally wants to go. All right, we discussed that we defined a coefficient of performance, and that coefficient of performance is different in cooling mode compared to heating mode. In cooling mode, what you get out is the heat that you remove from the low temperature reservoir, so it's QC over what you put in, which is the work, and then the coefficient of performance, let's see, and that is QC over QH minus QC. Coefficient of performance in heating mode is what you get out, which is the heat that you expel into the high temperature reservoir. So it's QH over QH minus QC. And then we thought, well, if we're an engineer, we want to make the coefficient of performance as high as possible. And the way we can do that is by getting the work as small as possible, which is to say, we try to get it to go all the way to zero. And so we imagine a perfect ideal, let me just draw it like this, an ideal heat pump, let's see here, which draws QC out of the low temperature and expels it into the high temperature without the input of work. The coefficient of performance would be infinite for this. And as you know, that never happens. You know, you never have heat spontaneously go from low temperature to high temperature. Something has to be done to get that to happen. And so Clausius realized this was impossible. And so he stated the second law of thermodynamics as exactly that. So this is also the second law of thermodynamics. This is the Clausius form after the person who discovered it, Clausius. Yeah, and it states that it is impossible to pump heat from a low temperature reservoir to a high temperature reservoir without the input of work. Okay, now our final topic. Oh, no, one more thing before that. Okay, we defined reversible and irreversible. We said that a reversible process is one where we can reverse the process all the way back to its original state without a change to the environment. So we know many systems that we can return to its original state, but we only do that when we change the environment in some way. Like we do work on the system, therefore we've used up some of our energy to do work on the system, right? Or if we keep the temperature of the system the same, then heat probably flows in or out of the system into the environment. So anyways, all processes in nature, including human-made ones, they're all irreversible. So all processes are irreversible. Um, and then Carnot, who was a person who studied the efficiency of heat engines, he found the maximum efficiency possible for a heat engine. And he did it by creating a theoretical heat engine called a Carnot heat engine, which runs on a reversible process. So as soon as you hear that, since it runs on a reversible process, you know it's not real. It's theoretical, but it still allowed him to find the maximum efficiency possible. And so he stated that the efficiency of a real heat engine is less than the efficiency of a Carnot heat engine. And the efficiency of a Carnot heat engine, he found to be 1 minus Tc over Th. Okay, so just the 1 minus the ratio of the temperatures of the reservoirs. So that puts a maximum value on the efficiency of a real heat engine, which as you can see is below 100%. So before this, you might have thought, well, even though the efficiency of a heat engine can't go above 100%, you might have thought you could get to 99% or 99.5%. But Carnot said, no, that's not possible, that the cutoff is actually lower than that. So for example, if the low temperature reservoir was 300 Kelvin and the high temperature reservoir was 600 Kelvin, then the maximum efficiency possible theoretically is only 50%. And that's kind of an amazing thing. For heat pumps, this translates into the coefficient of performance in cooling mode is less than or equal to Tc divided by Th minus Tc, and the coefficient of performance in heating mode is less than or equal to Th divided by Th minus Tc. So that also puts limits on heat pumps, and these maxes come because a Carnot heat engine, since it's reversible, you can reverse its process, and in reverse, it's a heat pump. All right. Our final topic is entropy. And we learned that the definition of entropy is Boltzmann's constant times the natural log of W, where W is the number of microstates for the particular macro state, right? So if you had the ability to count the number of microstates for a particular macro state, you could plug that in and get the entropy. Now, with a gas or something with 10 to the 24 molecules, order of magnitude 10 to the 24 molecules, the number of microstates that give you the same temperature, pressure, volume, et cetera, number of moles of gas is ginormous. So you'll have a very difficult time actually counting them. But what we actually usually care about is the change in entropy. So the change in entropy, the differential change is dQr over the temperature. And therefore, the total change in entropy is the integral from the initial state to the final state, dQr over the temperature. And the R, what does the R stand for? The R stands for that we have to do this calculation along a reversible path. Now, we're not claiming that this is a real path, but what we're claiming instead is that the entropy, okay, let me make this point. Entropy is a state variable. So what that means is it does not depend on the path, okay? So that's kind of like other state variables. So temperature is a state variable. So if I ask you what's the difference in temperature between today at noon versus yesterday at noon, you do not need to worry about the path between those two times. You just look at the temperature now on the thermometer. You look at what the temperature was recorded as yesterday at noon. You take the difference, you're done, right? You don't need to worry about whether during the night the temperature of the building went down first and then came back up, or whether it went up and came back down, doesn't matter. The difference in temperature is the same, right? Okay, so state variables have this property. Same thing with entropy. Entropy only depends on the end states, the beginning and end state. It doesn't depend on the path in between. So that means that we can do this integral along any path that joins the initial and final point. And that is a very important thing to remember in order to actually calculate this in real systems. So if the temperature starts at, say 300 Kelvin, and then it increases to 700 Kelvin, and then it drops back down to 300 Kelvin again, well, the initial temperature and the final temperature are the same. Therefore, you're allowed in that particular case to hold the temperature constant during the integral of the change in entropy. And so you could pull it out of the integral, and it would be just the amount of heat going into and out of the system divided by the temperature, the constant temperature, even though the temperature is not actually constant for that process. Now, on the other hand, if the temperature goes up to from 300 to 700 Kelvin, and then it drops down to 400 Kelvin, then the initial and final temperatures are not the same. So therefore, you cannot just simply pull the temperature out of the integral because um, because the temperature changes during, between the initial and final state. So you're going to have to find a different path. Okay, so the point is you find an appropriate path for your integral. Any path is fine. It does not have to be the actual path followed by the system. You find any path that matches the initial, that connects the initial and final point, and that path is allowed, and then you can calculate the change in entropy. Okay, then finally, our final thing is to restate the second law of thermodynamics as the entropy of any system plus environment always increases. And this is an important statement. There's never been a time where the entropy of the system plus the environment did not increase. There are times when the entropy of the system decreases, but then the change in entropy of the environment increases, and the amount it increases by is greater than the amount that the entropy of the system decreased, right? So the total is always increases. So even though humans have a lower entropy than our surroundings, it's only because we're constantly increasing the entropy of the environment around us. So taken together, a human plus the environment, the total entropy increases. And that's the thing to remember with entropy. Okay, now this is our final statement of the second law of thermodynamics. So the final thing I'll say is that this statement, it turns out, encompasses the previous statements of the second law of thermodynamics. So it turns out that this statement implies the Kelvin-Planck form of the second law of thermodynamics, and it implies the Clausius statement of thermodynamics. So this one is general enough to encompass all of the second law of thermodynamic phenomena. Okay, that's it. Good luck on the test, and make me proud.